Today we'll be working on the following problem. Let A and B be two subsets of Rn, the n-dimensional Euclidean space with the Lebesgue measure M and the Lebesgue outer measure M star. Now suppose that the union of A and B is measurable and the measure is a finite number. Now, if we have this relation, the measure of the union is the sum of the outer measure of A and B. Then we want to show that both A and B must be measurable, Lebesgue measurable. Pause the video if you want to work on this problem by yourself. Okay, let's see how to prove this. So from the condition, like you have A and B, right? And then the union, the measure of the union is the sum of the outer measure. So we can see like it's very likely the intersection of A and B must be of measure 0, right? So, but this is what we haven't proved A and B are measurable yet, so we can't really see this. But the outer measure is likely to be 0. So let's first verify this, because we know from the Lebesgue measure theory, like we can find we have a measurable cover for A and B. That is to see we can have a G and H a measurable subset of Rn, where G covers A and H covers B. And then they have the property like the measure of G is the outer measure of A, and the measure of H and is also an outer measure of B. All right. So now we want to find what is the intersection about what is the measure of the intersection of G and H, and then that is to tell like the intersection of A and B, right? So by assumption, we have this plus the outer measure of B. This is the measure of A union B, right? That's the assumption. But this is clearly less or equal than the measure of G union H, right? Because a subset. But now since G and H are both measurable, so we can use them. They have the additivity, so which means it is M of H, M of the measure, and then minus the measure of the intersection, right? And then this is what? Again, because G and H are measurable cover, and they have the measure is the outer measure of M star of A plus the outer measure of B minus this. So we have this is less than or equal to this minus this. This implies, because the measure is always a non-negative number, right? So this one has to be 0, and which means the ultimate, of course, A and B, the outer measure of A intersect B, it's also 0, right? So we can use that. So okay, now we want to prove A and B are measurable. So what we want to show is like for all t, we want to prove that the outer measure of t is the outer measure of T intersect A plus the outer measure of T intersects the complement of C, right? Complement of A, and this is what? This is the Theodori criteria. So based on this, if for OT we can prove this, then A is measurable, right? So let's work on this by using the condition. The M of A union B is the sum of the order star. So now we can write in this format. We can write down. So on the right hand side, A intersection. We first write down. We can okay. Let's see, T intersect A, right? And now we split this T intersects A complement to be like this. We want to use the condition B, A union B, right? So this is clearly T intersect the B, the complement, and then this is less or equal to, right? Because this term, when you split into the union of these two, so it is the outer measure is less or equal because the subadditivity, and then this equal to plus complement B, and then plus, and then we just rewrite this T intersect A union B complement, right? Okay, so let's see what about this? And now we want to use the cover. So this is exactly a T. And then we want to use this with the cover. And this first we make it this less or equal than T union B, right? This, and then plus intersects this, the complement, because this is clearly a subset of T intersect B. Now we write in this format. We want to use the condition is A plus. We now split this into because G is measurable, right? So let's write down this. Intercept the G complement, and then plus, we write down the same, A union B, right? So because G is, so we use the Theodori criteria applied to T intersect B. The reason we are doing this is like if you look at this term, now B intersect G is contained in H intersect G, right? So now we already proved the measure of G intersect H is 0. So and this is clearly a subset of this. So this term disappeared. This term is 0, right? And now this 2, remember we have T intersect A is a subset of T intersect G because G is the cover. And then this is clearly a subset of G. And now this T intersect B into G of C, it is a subset of the complement of C, right? So now, you know, this G and the G complement, of course, they have no they are the disjoint. They're disjoint. Now from problem, the previous problem 9, we have this two subset are separated by a two disjoint measurable set, right? So then the sum of the auto measure is equal to the measure of the sum, the union in the G of C. And then we just rewrite the last term, T intersect A union B complement. Okay, and then this is also a subset of T intersect B. So this is at most, and then union T intersect B, and then the last term we rewrite as T intersect A union B complement. And what is this? It is T intersect A union B, all right? The complement. Now now again we're using the A union B is measurable, and this sum is exactly the auto measure of T because of the Carotheridory criteria, right? So what we have proved, so this the auto measure of T intersect A plus the auto measure, that is this one is less or equal than this, but the other direction is obviously, right? So therefore is we have this A is measurable, right? And then the same for same for B is the same. We're done.